sides here. So, like I've been introduced, my name is Sifundo Gumede, and I'm a lecturer at Mangosuthu, University of Technology, and I'm lecturing mathematics there. So what I'll do now is I'll close my camera and start presenting. All right, so I hope that you have had a very fruitful week, all of you grade 10 learners. And then the way I designed this lesson is that it becomes a bit easier in a sense that I'll start from the beginning and try to recap different trigonometric ratios. Hopefully you've seen them before, so we'll try to recap them. And then the next thing that we'll do is to try and solve basic trigonometric equations using the trigonometric ratios that we'll have discussed. And then the last thing that we'll do, hopefully time will not be against us, would be to define trigonometric ratios in a Cartesian plane now. Right. So I found it interesting that trigonometry is introduced at grade 10, because if you grow up with these basics, by the time you reach grade 12, you'll be a very well-oiled machine. All right, so I'll begin with the definitions here. So remember that trigonometric ratios or trigonometric functions are defined in a right-angled triangle. So it means that for you to define these trigonometric ratios, you must have one of the angles in a triangle as 90 degrees. So always check that before you define the ratios, that one of the angles is 90 degrees. So you see that in this triangle, we've got sides AB, BC, and AC. And then we've got an angle which is 90 degrees. And then here I put an angle theta. So I'll be using this angle theta to define the ratios. But of course, another person can use a different angle. So you can use any other angle except the one that is 90 degrees. So just a recap. With respect to the angle theta here, we can define our sides. And always we'll define our sides as opposite, adjacent, and hypotenuse with respect to the angle theta. So there's 90 degrees here. So always a side that is opposite, it's just opposite to 90 degrees. We'll call it hypotenuse. So this side that is always opposite 90 degrees, we'll call it hypotenuse. Right. And then if theta is our angle here that we are going to use, the side that is opposite, this is opposite, you can say direct opposite, will be called opposite. So because it is opposite to our angle theta here. So it means the side here where theta lies, we'll call it adjacent. This is adjacent and opposite and hypotenuse. So when we define our trigonometric ratios, there are three basic ones. There's sine of an angle theta. There's cosine or cos of an angle theta. Then there will be tan of an angle theta. These are our three basic trigonometric ratios that we'll define using these sides of a right-angled triangle. So sine, I hope you'll remember that there's something that we called that we use when we define the trigonometric ratios. So when we define sine, sine will be opposite over hypotenuse. So sine of theta will be opposite of our theta, which is AB. So AB is opposite of our angle theta over hypotenuse. Hypotenuse is BC. So sine theta is opposite, which is AB, over hypotenuse, which is BC. So when we define cosine, cosine is, so it's car. So it's adjacent, which is AC, over hypotenuse. Hypotenuse doesn't change, it's still BC. So we define cos theta as adjacent over hypotenuse. Yeah. And then we'll define tan of theta. which is opposite. Opposite is AB over adjacent. Adjacent is AC. AC. So these are basic trigonometric ratios. In fact, it doesn't matter whether you go to grade 11 or grade 12 or straight to university, you'll be using these definitions. These are very important to remember in a right angle triangle. And another thing that I wanted to talk about. So it's always important to remember the SOHCAHTOA rule. SOHCAHTOA rule. And another thing that I wanted to talk about is what is called the reciprocals of this. So these are three basics, and they've got what is called reciprocals. Reciprocal ratios of these three. So each ratio has its corresponding reciprocal. So when you say reciprocal, it means it's a ratio such that it's 1 over this. So 1 over sine theta. So it's a reciprocal of sine theta is called cosec theta. 1 over sine theta is cosec theta. So cosec is a reciprocal of sine. In fact, instead of saying sine is AB over BC, you can just say cosec theta is BC over AB. You can just swap like that because it's a reciprocal. Similarly, cosine, of course, has a reciprocal. That reciprocal is called sec. So 1 over cos theta is sec theta. So sec theta is a reciprocal of cos theta. Also, 1 over tan theta is equal to cot theta. Cot theta. So these are basic trigonometric ratios. But of course, if you know how to define sine in terms of opposite of hypotenuse, of course, cosec should be hypotenuse over opposite. So on. Same thing as cos theta, if it is adjacent over hypotenuse, it means sec theta will be hypotenuse over adjacent. So I thought it's better to start with that. And again, I'm still emphasizing that for you to define this, the triangle must be a right angle triangle. So you must be able to see where is your 90 degrees so that the side that is opposite to your 90 degrees will be your hypotenuse. Otherwise, you'll not have a hypotenuse if you don't have a 90 degrees. So that is the first thing that I wanted us to look at. Right. So just to emphasize this, the understanding of these ratios, I thought we'll go and try to do some problems here. Just to emphasize this. Now we know the definitions of the trigonometric ratios. Can we use these definitions to find the length of the unknown sides? Right. So what I have here is a triangle. What is nice about this triangle is that it is right angle. So there is a right, a 90 degree angle here. So we want to use that to find the unknown. So the angle that we'll be using here is our angle 50 degrees. So what we need to do is to say, okay, this is 90 degrees. So it means this side that is opposite to 90 degrees is our hypotenuse, right? So what is x? X is the length of a side. And how is this side related to our given angle 50 degrees? So you can see that this side is opposite to 50 degrees. If it's 50, this is opposite. So in relation to 50, this is opposite and this is hypotenuse. And then you think about which trigonometric ratio relates opposite and hypotenuse. Then you remember, so opposite of hypotenuse. So it's sine that relates opposite and hypotenuse. So it means sine 50 degrees, because we're using 50 degrees now, is opposite over hypotenuse, right? That is what we have. So we say Sine 50 degrees. We know our opposite is x in this case. That is what we want to solve anyway. And our hypotenuse is 100. And we want to solve for x. And remember, if we want to solve for x, it means we don't want to have this 100 here. So it means what will we do? We'll multiply by 100 both sides, because this 100 is dividing here on the right. So we'll multiply by 100 here. So it's 100 times sine 50 degrees equal to x. Because if I say times 100 here over 100, so this will be 1. So x 100 times sine 50 degrees is equal to x. And then you can take your calculator and find out what is 100 sine 50 degrees. So according to my calculator here, it should be 76.6 x. If you like, if you want to start with x and end with this, you can just interchange the positions here. But anyway, it does not matter. Whether you say 76.6 is equal to x, or you say x is equal to 76.6, it does not matter really. Right? So you see here, just to recap, what we did was, we said we want to find the length of this side, but the angle that we know besides the 90-degree angle is 50 degrees. So that side is opposite to our angle 50 degrees. And the other known side is hypotenuse, which is 100. So we thought about what trigonometric ratio relates opposite and hypotenuse. We said if we use our soccer tool, it's sine. So sine is opposite, which is x, over hypotenuse, which is 100. And then we got the length of the side, x, which is 76.6. Right. I hope that that is easy and straightforward. If in case maybe you missed that a little bit, you want me to do another example, I'll go for number 2, which is similar. We're finding the length of the unknown side. We want to solve for y. Same thing applies here. This triangle is right angled. So there is a 90-degree angle here, and then the side opposite is y, the y that we want to solve. So now what we need to do is to say our angle that we know here is 25 degrees. And the side that we have here, how is it? Is it opposite or adjacent to 25 degrees? Of course, it's not opposite, because opposite will be here. It's adjacent here. Adjacent to 25 degrees. So it means we've got adjacent, which is 7, and hypotenuse, which is y. So which trigonometric ratio relates adjacent and hypotenuse? So it is cos 25. So cos 25 degrees. Cos 25 degrees is adjacent. Adjacent is 7 over hypotenuse. Hypotenuse in this case is y. And we want to solve for y. So what you can do here is to multiply by y both sides. So it means we'll have y here, cos 25 degrees is equal to 7, because if multiplied by y, this y would be dividing this y. So we'll have y cos 25 degrees is equal to 7. So now, what we can do is to say, we want to solve for y. So what can we do? We want to solve for y. The problem that we have is this cos 25. So you can divide by cos 25 degrees, both sides. So that cos 25 and cos 25 we divide each other. Then we have y equal to 7 over cos 25 degrees. Right. So now we've written y here which should be 7 over cos 25 degrees. So all we can do now is to try and use our calculators. So I got 7,72. So y is 7,72. It's a length of y. So again, to recap what we did, we said this our angle that we have is 25 degrees, and 7 is adjacent to that angle, and y is opposite to 90 degrees. So it means we've got adjacent over hypotenuse. So that means it's cos of an angle, which is adjacent of hypotenuse. That is what we have here. And then we cross multiplied this and that. We got y equal to y cos 25 equal to 7. Then we divided by cos 25 both sides to get y explicit. And then we got 7,72. Right. So this was a second example, just to stress the relationship cos of an angle, hypotenuse, adjacent, and so on. I'll try to be fast here because I think we still have to go to other things. I think it's just almost a repetition of a similar thing. It's just that here we've got two unknowns, x and y. So it means we can start by solving for x and then go for y. It's up to us. So maybe let's start with x. So what we have here is that we want to solve for x. So are we going to use sine, cos, or tan? And we should be clever about this one because with respect to 25, this is opposite. This is adjacent, this is hypotenuse. So the point that I want to make is that if we think that we are going to use opposite over hypotenuse, we are going to have x and y all unknowns. So it means that when we try to solve for x, in a way we must use 7 so that we don't have an unknown. So if we solve for x, we must use 7 so that we'll have x only, which is unknown. So if you look at it, with respect to this 25 degrees, x is opposite and 7 is adjacent. So which trigonometric ratio relates opposite and adjacent? We'll say that is tan. So it means tan 25 degrees is opposite of adjacent. Our opposite is x. Our adjacent here is 7. So like I said, the reason why I'm running away from using hypotenuse is that we'll have x over y and have two unknowns, which is what we don't want to have. And then when we cross multiply or multiply by 7, both sides, it means we'll have 7 times tan 25 degrees equal to x, right? And then we can evaluate what is 7 tan 25. So I'm getting 3,26 equal to x, right? Or x equal to 3,26. That is how we found x. Now, when we try to find y, again, we'll do the same thing. In a way, we have to use this 7. So we said this 7 is adjacent. And then y now is hypotenuse. So adjacent over hypotenuse. Which ratio is that? It's cos. Hypotenuse is y. Y. So I'll cross multiply again and say y cos 25 degrees is equal to 7. Like I said, I'm trying to be fast now. And dividing by cos 25, both sides. I will have y equal to 7 over cos 25 degrees, which I will evaluate using my calculator. 7 over cos 25 degrees. We've got 7,72. So in fact, example 3 was just combining the first two. trying to say that if I've got two unknowns in a single triangle, what do we do? Unlike in examples 1 and 2, we had one unknown. So like I said, we have to be clever here and use the side that is known and one unknown. Right. I hope this is still straightforward for now. Right. And then let's see what we have next. What we have next is, now in the past examples, we're using trigonometric ratios to find the length of the sides. Now we want to use it to find the size of an angle. So now we want to find the size of an angle theta here. Right. I hope my internet is still stable. Right. So what we have here is that we've got theta here that we want to find, and we've got sides which are known. And the sides are, with respect to theta, these are opposite and adjacent. So which trigonometric ratio relates opposite and adjacent? Obviously, it is tan theta, which is opposite over adjacent. So in this case, tan theta, our opposite is 50 over 100, right? 50 over 100. So all we have to do now is to try and find theta. So how do we find theta? We'll use our calculators. So I'm using a Casio calculator here. I hope that most people are using it. So I'll press, if I want to find the angle theta, I'll press shift in a calculator. Shift, then I'll press tan because I've got tan here. Tan button, and then it will open the bracket. Then I'll press 50 over 100. So it's 50 over 100. Then I'll close the bracket. Then I'll press equal to. Then I got 26,6 here, right? This is an angle. So I'll say now my theta is 26,6 degrees. It is the size of my angle theta. So again, to recap, we said, okay, this is our angle theta that we want. The sides that we have with respect to theta are opposite. This is opposite to theta and adjacent. So the trigonometric ratio that relates opposite and adjacent is tan theta. This is why we said tan theta is 50 over 100, opposite over adjacent. And to find theta, we press shift, tan, then in bracket, whatever that we have on the right-hand side, and equal to, then we get 26,6. So it means our theta is 26,6 degrees. Because it's an angle, we need to leave it as degrees. We can do the same thing here, number 2, and say our angle theta. Which sides do we have? The sides that we have are, this is opposite to angle theta. Opposite to angle theta, this is hypotenuse because it's opposite to 90 degrees. So which trigonometric ratio relates opposite and hypotenuse? So opposite hypotenuse, so it's sine. So sine theta is opposite, which is 7,5 over hypotenuse, which is 13, right? So we'll do the same thing again. We'll press shift in our calculator, shift, and then sine in this case, and then sine. And then inside the bracket, we'll press 7.5 over 13, close bracket. 7.5 divided by 13, close bracket, and equal to 35,23. So it means our theta is 35,23 degrees. So it's just a matter of saying which sides are known, and it's opposite of a hypotenuse, you know its sign, and so on. So this should be very straightforward. So it's just a matter of using your calculator here in our right-angled triangle. Right. I think this is straightforward. Let's go to solving the unknown. Solving the unknown here. So here, what value of theta satisfies following a trigonometric equation? So it's a trigonometric equation because it consists of a trigonometric ratio sign. So what value of theta satisfies this? So the problem that we have is this 3 here. We don't want to have a 3. We want to have sine theta equal to something like we had in the previous page here. We had sine theta equal to something. We don't want to have a coefficient for sine theta. So the first thing that we want to deal with is to try and get rid of this. So to get rid of it, it means we divide by 3, both sides, right? It is the first thing that we'll do. We divide by 3, both sides. And when you divide by 3, both sides, it means we'll have sine theta equal to 2,4 over 3. So now, again, we'll do the same thing, that shift sign, (2.4 over 3). 2.4 over 3. I got 53,13. So it means theta is 53,13 degrees. So it means that is a solution of this equation here. So a solution of this equation is 53,3. That is the theta that satisfies this equation. And if you have got time and you want to check if your solution is true or not, all you have to do is to say 3 sine and put 53,13 in your calculator. It should give you something equal to 2,4. Could be 2,4 exactly, or 2,3999 something, but it is very close to 2,4. So that is how we solve. So we solve as we were using same technique that we used in a triangle. We use it in an equation here. Right. Same thing applies here. It's just that we are solving for alpha here. So we divide by 4, so that cos alpha is equal to 3 over 4. So I won't write now, but I'll just say that you press shift cos and then 3 divided by 4. And then I got 41,4. Alpha is 41,4 degrees. Right. So we use the same thing that we're using there, 41,4 degrees. Now, I think this one would be interesting. This one would be very interesting, and you'll see why it's interesting. Same thing will apply. We'll divide by 2, both sides, so that you'll have cos beta equal to 2,4 over 2. Right. So it's 2,4 over 2. So what I'll do, I'll say shift, just writing shift, cos 2,4 divided by 2. So shift cos 2,4 divided by 2. What am I getting? In my calculator, I see math error. So it doesn't want to give me an answer here in this case. Right. So it means now this equation does not have a solution. So there's no value of an angle beta which will satisfy this. And the reason why that is the case is that, you see this side here, our cosine function, same as the sine function. Our cosine function of any angle must be less or equal to 1. Less or equal to 1. Right? So it means if this number here is bigger than 1, there will be no solution here. Right? So it means even if I can just give you an equation and say cos theta is equal to 2, for example, you can quickly look at it and say, no, if the right-hand side here is more than 1, then we'll not have a solution. So it means a cosine function, same as sine and also sine function, is always less or equal to 1. So it means, but if you couldn't see it from the beginning, anyway, you'll just press shift cos, and when you get a math error, you'll say, okay, there's no solution. So this equation cannot be solved. There's no beta that satisfies this equation. Right. I hope that is clear and very straightforward, that not all trigonometric equations will have solutions. So if you get a math error, it means there's no solution. There's nothing wrong about that. Right. That is number 3. Let me see what we have here in number 4. Number 4, right. We're doing the same thing. It's just that now I've made 2 terms on the left. So what we want to have is, we want to have sine theta equal to something. Right. We don't want to have something as complicated as this. So the problem that you first want to deal with is this one. We don't want to have too many terms on the left. We want to have 1 term. So the problem that we have is this one. So how do you deal with this one? You subtract 1 both sides. So when you subtract 1 both sides, so this will be 2 sine 3 theta. Because there's this one, then there's minus 1 that you are going to put 2,6 minus 1. In some cases, they call it, you just take it to that side and transpose, but same as saying we're subtracting it both sides. So we'll have 2 sine 3 theta. This 2, 1 minus 1 should be 0. And then we'll have to calculate what is 2,6 minus 1. I got 8/5 or 1,6. Got 1,6 here. So what we'll do now next, you see that there's a problem of this 2. You divide by 2 both sides. Then we'll have sine 3 theta equal to 1,6 over 2. And you do the same thing that we did. The only difference is that we don't have theta here, but we have 3 theta. So it means now it's your 3 theta that should be equal to, then you press shift sine, then 1,6 divided by 2, as we did previously. It is equal to 53,13, right? Degrees. It's your 3 theta, not theta. So it means theta is equal to 53,13 degrees over 3. So theta is equal to, then you find out what is that using your calculator. 53,13 over 3. I'm getting 17,71. 71 degrees. So what was special about this example was that, first of all, we have to deal with this one by subtracting it on the right? So it's 2,6 minus 1, because here you just subtract this one, should go away when you subtract with this one. Here it should give you 1,6. And then you divide by 2 both sides. Divide by 2 both sides, you get 1,6 over 2. And then remember, this is sine. If this was just theta, we'll say theta is 53,13 and so. But this is 3 theta. So we'll say this whole 3 theta is, we press shift, sine, and we put this. We get 3 theta equal to 53,13. And then we divide by 3 both sides. We get 17,71 degrees. Right. Maybe number 5, maybe we can just say, take these 2 that side. So it's sine beta equal to 2,65 minus 2. I think I was supposed to do number 5 before number 6 because it looks like it's very easy. So sine beta is equal to 2,65 minus 2. What is that? Is 0,65. And then beta is equal to, becoming fast now, you press shift, sine 0,65 equal to 40,54 degrees. Like I said, if you want to check, you can just put sine 40,54 degrees plus 2 in a calculator, you must get 2,65. But I wanted to do number 5 because before number 6, it looks like number 5 is easier than number 6, but we are doing the same thing. Right. Okay, just to close off this, these equations, I thought I should go to this one. This one is interesting just because it has sec, which is a co-ratio. Remember, sec is a reciprocal of cos. So remember, what we need to do is, we are used to cos and sine. So what we need to do is to just change and say, instead of dealing with sec, it's 3 times 1 over cos. It would be better if we deal with cos than to deal with sec because we're used to cos in our calculators, right? Then what we'll do, we'll cross multiply by cos both sides. So we'll have 3 equal to 1,4 cos theta, right? And then 3, we divide by 1,4. 3 over 1,4 is equal to cos theta. Then I'll press my shift cos, I'll put 3 divided by 1,4, and then I'll get a math error. So I'll get no solution. No solution, because if I press shift cos and I put 3 over 1,4, I got math error. So it means the equation does not have a solution. So just to recap, if you see sec or cosec or cot, if you see one of those reciprocals, it is better to just change sec to be 1 over cos theta, because you know it is easy for you to deal with cos in your calculators. So it's 1 over cos theta, and multiply by cos both sides, we got 3 equal to 1,4 cos theta. Then we divide it by 1,4 both sides. And then we said cos theta is equal to 3 over 1,4. And then when we divide it, when we press shift cos 3 divided by 1,4, we got math error, which means there is no solution here for this equation. Not because there's sec, but it's just that there's no solution. Because the reason is this number here. See this number, if you can just say what is 3 over 1,4, you'll see that this number is bigger than 1. So of course, if this number is bigger than 1, we just said before that cos theta is always less or equal to 1. If the number on the right-hand side is bigger than 1, then we will not have a solution, obviously. Right. So that is basics of solving trigonometric equations. I think as time goes, we'll learn to solve more challenging ones than this, but these are the basics that you'll need. Just to press shift sign if it is sign, shift cos if it is cos. Right. I think we've got 15 minutes now, so I'll try in the last part and see what can we do and see whether we can finish or we won't. But even if we don't, we'll try to cover. We'll hope that what we've covered is understood. You understood very well. So remember that in the previous pages here, we're defining trigonometric ratios in a triangle, right-angled triangle. So you can also define trigonometric ratios on a Cartesian plane now, right? So I made some examples here. Say, you can put a point. So I hope you remember that the Cartesian plane has the X and Y axis. Like this, so X horizontal, vertical. So you can put any point at any part of the Cartesian plane and then define trigonometric ratios using that point. So what I did here is an example that I put a point P here, right? Point P is having some coordinate, X is to Y, could be any number X to Y, right? So what we do here is we put a point, we draw a line from the origin to that point, right? And then we measure an angle from the positive x-axis to that line. So if you've got a point, even if we put a point here, you can draw a line from the origin to that point, and we can measure the angle from the positive x-axis to that line. In our case, this is our angle theta. So theta is measured from here to that line, right? And we want to define trigonometric ratios now of theta, where theta is measured from the positive x-axis to the line, OP. So what we can do, we can extend here and extend our right-angled triangle so that we can have hypotenuse. So we can extend our right-angled triangle here, right? So it means if this point is X to Y, so it means the X value for this point is X, right? So it means that the length from here, to this point here, we'll call it X. This side would be X. And the length from here upwards is Y, because the Y coordinate is Y here. So it means here is Y. So it's Y here, right? So it's Y here. So we can define trigonometric ratios of theta now in general. If theta is an angle here in this quadrant, these are quadrants of a Cartesian plane. So we can say that with respect to theta, what is sine theta? So sine theta would be opposite over hypotenuse. Oh, okay. Before I define it, I've forgotten that this side will be hypotenuse because it's opposite 90 degrees. And hypotenuse, we'll name it and say it's R. I hope you remember theorem of Pythagoras that if you've got a right-angled triangle, we can always find the length of hypotenuse once we know the other two sides. Like saying x squared plus y squared is equal to r squared. You can use it. You can use this Pythagoras theorem. As long as we have the right-angled triangle. If you've got other two sides, you can always find the hypotenuse. So it means sine of theta will be opposite. Opposite is y over hypotenuse, r. and cos theta is x over r, which is adjacent over hypotenuse. And then tan theta is opposite over adjacent, which is y over x. Although I won't write, but always you know that once you've got sin theta, you can always define cosec theta, you can always define sec theta as r over y as r over x. You can always define cot theta, which are reciprocals, as x over y. So these are trigonometric ratios in a Cartesian plane if we choose a point on a first quadrant here, this first quadrant of a Cartesian plane. And these ratios may change, may be positive or negative, depending on which quadrant is your point P on. If our line was in this quadrant, you see that our x would have been negative. And if our x was negative, it means that the ratio that contains x, like cos theta, was going to be negative. And also tan theta was going to be negative. So the ratios can be negative or positive depending on where your point is, right? I'll do the example so that you see. But what is important is that we can move our point P and put it in this quadrant or in this quadrant or in this quadrant and always define all these trigonometric ratios. In some quadrants, some trigonometric ratios will be positive, some will be negative, right? So, for example, here, remember that this quadrant, we call it first quadrant because you measure from 0 going this side, quadrant 1, quadrant 2, quadrant 3, quadrant 4, right? So in fact here, all the trigonometric ratios will be positive because x and y are positive. And here, only sine and its reciprocal positive. Here, only tan will be positive. Here, only cos will be positive. Because, like I said, sine will be positive here because sine is y over r, and y is still positive here. And so on and so on. So we call this a cast diagram. If you want to know which trigonometric ratio is positive where, you can use a cast diagram. And cast diagram means we start from the fourth, C-A-S-T, right? C-A-S-T, to check which trigonometric ratio is positive in which quadrant. So I hope you'll remember this cast diagram. So I'm trying to be fast now because we've got 5 minutes and do only one example to show you a case where you have got a point which is not in the first quadrant. Like for example, here, let's say that you've got a point P lying on the second quadrant. It's minus 3 to 4. So it's minus 3 x 4 as y, right? So we want to find trigonometric ratios for a point on the second quadrant. So the center is O, the origin. Theta is an angle between OP. So the point P is here, is minus 3 to 4, right? And the line OP is from the center to the point P here, right? And theta is measured. The angle is always measured with the positive x-axis. So theta is measured here. Theta is here, right? So what we want to find is we want to find cos theta and tan theta and so on. So what we do as we did in the previous slide. You extend your right angle triangle to the x-axis here. The nearest x-axis here are negative ones here, and create your right angle triangle. So what you know is that this side here, from the origin, 0 is to 0, here is 3, length is 3, because it's minus 3, and this side here is 4, right? because y is -4. But for you to find cos theta, you need to find adjacent side over hypotenuse side. If your theta is here, the adjacent side would be this side that we know. The hypotenuse side would be that side that is opposite to 90 degrees. So it means the first thing that we need to do is to find the length of hypotenuse, which is, you can use the Pythagoras theorem, which we said is r squared equal to x squared plus y squared. So remember, you want to find r, which is your hypotenuse. And your x is -3. This one. It's -3 squared. Your y is 4, which is 4 squared. So it means your r squared, in this case, would be 25. So what do you square to get 25? It's 5. So r is equal to 5. So this side is 5 units, right? So it means cos of theta is adjacent of hypotenuse. Our adjacent is, in this case, it's x over r. X over r. Our x would be our adjacent here, which is -3 over 5. So that is our cos theta. Okay, we're not required to find theta anyway, so we'll stop here. We just had to find cos theta. So it's just extending a right angled triangle here and define and find your hypotenuse, because you're given x and y. So this is your x, this is your y. X is -3, y is 4. But for cos, we needed x over r. Right. 2, we want 3 tan theta. 3 tan theta is equal to 3. Your tan is, you said tan is, you use y and r, is y over x here. Y over x here. So tan is y over x. So tan theta is y over x, our y is 4. Our x is -3. So 4 over -3. Right? 4 over -3. And we multiply this, we cancel that, we get that this is -4. So 3 tan theta is -4. Right. So just to recap here, if you are given a point on a second quadrant, it means a point that has negative x and positive y should be in a second quadrant. You put a point here, you draw a line from origin to that point, then theta will be from positive x-axis to the line. Then you extend your right angle triangle. Your x will be negative, your y will be positive. And then you use Pythagoras theorem to find hypotenuse. Yeah, r squared is equal to x squared plus y squared. So r squared is 25. And the square root of 25 is 5. I know that maybe you learned that it's plus or minus 5. The square root is plus or minus 5. But in this case, because hypotenuse is always a length, we always take a positive, not a negative. Right. Chairperson, I think I'm running out of time. I don't think I'll be able to finish number 3. What do you say? Oh, while the chairperson is still trying to talk, we can still do the same thing. Okay, yes, chairperson.
Dr. Sifundo. Oh, okay.
Yes, sir.
Or you can continue maybe for 5 minutes, then we'll wait for a question.
Oh, okay. All right. And then let me try to be a bit slowly now, since I've been given 5 minutes. So now, what we want to do is to try and find half cosec theta. Half cosec theta. is equal to what? Okay, half is here. So all we need to do is to write cosec theta in terms of x, y, and r. So we come back and say cosec. Cosec, remember, is a reciprocal of sine. Sine is y over r. So it means cosec theta is r over y. And we go back to our diagram. Say, so cosec is r over y, which is half times r. Our r, we found it using Pythagoras theorem here as 5. So it is 5 over our y is our y in our point. Y is 4, positive 4. So it is 4. So it means half cosec theta, 1 times 5 is 5. 2 times 4 is 8. So half cosec theta is 8. Is 5 over 8. So all that is important, guys, is that if you are given a point, locate that point. In which quadrant does the point lie? Draw a line from the origin to that line and extend your 90 degrees so that you have a right angle triangle, right, as I did here. And then you are given x, y, and y. You just have to use Pythagoras theorem to find your r. Once you've got x, y, and r, then you can find anything using the relationships that I just gave you on the slide above here, right? You'll stop me if. Okay, here we may not finish number 1 and 2, but just to show you that if you've got a point, say on another quadrant. So here, XOK theta is an angle on a third quadrant. X is a point on a positive y-axis, and K is a point, -5 is to y. So already we are told that we've got theta is an angle on a third quadrant. Third quadrant, which quadrant is that? It's quadrant 1, 2, 3, right? Just to draw this, I'll put, say, a point K here is a point, -5 is to y on a third quadrant. On a third quadrant, so -5 is to y. So a point K should be a point here, right? K -5 is to y here. So we'll extend our 90 degrees. Oh, also, I think we're given something else. OK is 13 units. So luckily here, we are given that OK is 13 units. So extend again in our x-axis, on the x-axis, extend a 90 degree. So it means OK is 13 units. And OK, remember, is our hypotenuse. And our angle theta means would be an angle like this, right? Our angle theta will be an angle like this because it's measured from the positive y-axis to the line, okay. So now what we want to do is to find the value of y without using a calculator. We want to find the value of y without using a calculator. So how would you find the value of y? We'll say, okay, we know hypotenuse, we know the length x, all we don't know is y. And we remember that there is Pythagoras theorem, which is r squared equal to x squared plus y squared, right? So what we want is to find y squared. We can make y squared
Dr. Gumede, I think you are breaking.
a subject.
Dr. Gumede, I think you have a network connection problem. Okay, I think we just lost Dr. Gumede. So if you have a question, you can type it on the chat box, then I'll answer you. But thank you for attending this lesson. You may come back at 12. We have a science show. So now we'll wait for our next presenter, which will be a grade 11 lesson. So do we have Mr. Mkhize?
No, our next presenter has joined us. It's Sinethemba Maduna.
Oh, okay. Miss Matuna, can you please share your screen so that you can confirm if we can see it?
Morning, Miss Maduna.
Okay. Njabulo, who's greeting in the chat. Oh, Snenhlanhla, I think we have Mr. Mkhize. It's supposed to be Mr. Mkhize. Can you please make him a co-host?
Sorry. I thought we were doing grade 12.
Oh, yeah. It is still grade 11. So please make him a co-host.
Apologies, Mr. Mkhize. I thought we were doing grade 12. Sorry for that.
Okay, morning, guys. I thought I put my background nicely where it's not showing. Thank you. Sorry about that. Maybe you're more than ready to present Sneh. But anyway, I'll be showing my face for 1 minute or so, and then because I'll need to write on screen. I think, could you please allow me to hide my face, then try to share my present.
Yes, I've made you co-host that you can share your screen and close your video. It's okay.
I hope you can see my screen.
Yes.
Beautiful. So I'll try to hide on screen, especially I'm solving these examples. But thank you for this opportunity. Let's hope that this lesson will benefit all the learners, everyone who's attending. My name is Njabulo from the University of Zululand. I'll be presenting trigonometry to grade 11. I think I should just start if that's fine.
Yes, that is fine.
Okay. I'm trying to actually miss some controls here. Sorry. So, okay, this is trigonometry for grade 11. So I started with just a brief definition. So it's my brief definition of trig here, which is an area of mathematics that is dealing with relationship between sides and angles. So we'll see sides and angles definitely. So let's look at the content then. Let's look at the content. I'm trying to make sure it's big enough so that everyone can see. So this is the content that I'm intending to cover for this presentation. The first one is trigonometric ratios definition. So that's how we define trig ratios. And then the second one will be trigonometric ratios behavior. Then we'll look at by quadrants, how are these ratios behave in terms of quadrants. Then we'll look at the reduction. So that's when we'll be looking at how to express trig ratios and non-acute angle in terms of ratio angle. And then we'll go on and look at negative angles. How do we deal with negative angles? And then the next one will be angles greater than 360 degrees. And then the last, I made this on purpose, which is four functions. That's the interesting topic that we need to cover there. So for definitions, you might have seen these ratios before. We've got 3 of them, and they are reciprocals, of course. But how do you actually define them? Let's look at how do you define them in a Cartesian plane. This is an XY Cartesian plane. So you have to actually construct a right angle triangle. That means you should have a triangle. One of the angles of that triangle should be 90 degrees. As you can see there, that's your 90 degrees there. That's why this one is regarded as right angle triangle. So they have it has those that property of 90 degrees as one of the angles. So you can construct it like that, and then probably you know that on your horizontal axis here, it's defined by all these values that you have horizontal here. Those are x values. And then when you go up here, those are the values of y. So we do have struck this such that we have an angle, then the angle theta, we can call it theta, or you can call it whatever. That angle that is formed there for that right angle triangle, in this case, we can call it theta. Then we want to define these trigonometric ratios. Just mentioned that the first one will be sine theta, the second one is cosine theta, the third one will be tangent, which is tan theta in short. And then there are reciprocals of cos, which is cosecant, secant, as well as cot. And then, so of course, you will have a right angle triangle. You can have a point there. That's fine. Let me just increase this a bit. So you can have a point there, call it P if you want, which defines or which gives you X and Y. So if you look at this point, which is that when you go up from the origin, which is, we call it O, 0, 0 there. If you go up there, you go Y unit up. So you can have that as Y unit up. And if you go that direction horizontally to that side, you go X unit. So that's how it is. And then this side is known to be our hypotenuse side. This is the R, that one. This is our R. So from there, you can think of a famous theorem, which is Pythagoras theorem, that relates all these X, Y, and R. R is our hypotenuse, that's the radius. Of course, how come this can be understood as radius? you can construct, obviously, or a quarter of a circle there. It's clear that that's a radius if you have a circle at 0, 0. So, but let's define the trig ratios using that. The trig ratios are defined as opposite over hypotenuse. That is sine. So we know sine is defined as opposite over hypotenuse. That is the opposite side to our angle theta. So this is the side that we're looking at. And then when you look at the side, when we define cosine now, we define cosine as adjacent side to our angle over hypotenuse. So what is adjacent to our angle? That's adjacent side, that is defined by x. And then when you go to the tangent now, tangent is defined as opposite side over adjacent side. So what is that? Our opposite side is given by y, and then our hypotenuse side is r. And then same goes to cosine. We look at the adjacent side, which is given by x, and then have hypotenuse side, which is the radius. And then lastly, it's going to be the opposite side, which is given by y, divided by adjacent side, which is x. And then we have, of course, the reciprocals, the cosecant, secant, and cotangent. The cosecant is a reciprocal of sine. That means we can just flip the value that we have that is defining sine. As we have y over r, we'll end up having r over y, as you might have seen. So that means for secant, you can have r over x. And then for cotangent, you have x over y. That is how you define your trigonometric ratios. But now I want to shift the focus to how do they behave per quadrant. That is very, very crucial to understand that when you're solving these kind of problems, actually, that involve trig ratios. How do they actually behave? So how does sine behave in the first quadrant, second quadrant, third quadrant, and fourth quadrant? Same goes to how does cosine behave in the first, second, third, and fourth quadrant. So of course, we have our first quadrant here. This is our first quadrant. I'll just put I, indicating the quadrant is the first one. And then the second one will be that. And then the third one will be that. And then lastly, the fourth one is that. But in your first quadrant, you want to actually see how does sine behaves, how does cosine and tangent behave. So if you look at first quadrant, you know that in a Cartesian plane, in the first quadrant, x and y are both positive. So if you were to define sine, you'll have, remember that you'll have y over r, as you can see from, so this is y over r. But remember r, from the construction that you have here, is the radius. So radius can be negative. So let me just write the famous theorem here so that you can always remember. R squared is equal to x squared plus y squared. That's the Pythagoras. You'll always have to remember this relationship. This is known as Pythagoras theorem. So this is what will help you to solve most of the problems as well. So in your first quadrant, then how does sine behave? You go back and just check. Sine is defined as opposite of a hypotenuse. That means you'll have y over r. And then you have y in the first quadrant. Y is always positive in the first quadrant. So everything that we look at will have positive y somewhere here. And r is always positive. This simply means the sign will always have a positive result here. So the sign of angle theta lies here, and then we'll have plus, which is the sine theta in the first quadrant. And what will happen to sine? The same reasoning will take you to sine being always positive here. Why? In the first quadrant, x is always positive. And then you move to the tangent. Tangent is defined as y over x, that is opposite over adjacent. As I just mentioned, x and y are both positive here. So if you divide y and x, a positive result with a positive result, you'll end up with a positive result. And then moving to the second quadrant now, how does the sign behave in the second quadrant? If you look at the definition again, always remember definitions. Sine is defined as opposite of hypotenuse. That means it's an opposite side of an angle divided by r, which is your hypotenuse side. So hypotenuse is always positive. So let me go back and indicate that this guy is always positive. That's your hypotenuse side, or that's your radius if you construct this. So remember, always remember that. So here it simply means sine, because sine is defined as y over r, then you know that here, second quadrant, in this portion here, y is still positive. So you have a positive result divided by r, which is always positive as well. So it simply means you'll end up with a positive result for sine. Going to the cosine now, things will change. Why? Because cosine is defined as x over r. So that means here in the second quadrant, you'll have negative values of x. So if x is negative, knowing exactly that r can be negative because it's our hypotenuse, and then it simply means here the cosine is negative. And then we move to the tangent now. Tangent is defined as opposite side over adjacent. So what is your opposite? Given by y. Y is always positive here, up here, above this horizontal line. So how about x now? X is negative when you move that direction. So it means we are dividing a negative result with a positive result, dividing x with y. So it means the tangent is negative there. Then moving to the third quadrant, to apply the same technique, think about definitions, you realize that here we'll end up with a negative sign. So sine theta there will be negative because sine is defined as opposite over hypotenuse. And y here is negative. Once you go beyond this origin, which is 0, 0 point, you go down, you'll have negative y values. Then you move to cosine again, same use definitions, and x over r in this case, x is negative on this pillar of this Cartesian plane, and then that means you'll say that negative value divided by r, which is always positive, then you'll end up with a negative result. And then same goes to tangent now. Now the tangent is very interesting because now you look at this and you understand that x is negative as you start from here to the negative side of the number line. And then if you start from here downward, y is also negative. That means we're dividing negative and the negative, then we'll end up with positive result. Then fourth quadrant, same technique or same understanding of definitions should give you a negative result of sine. And then the cosine should be actually that. Why cosine is positive? We think about the definition again. What is the sign of X values in this quadrant, as we're looking at from this line towards the positive side. X values are positive. So we'll have a positive, which is X divided by R, which is always positive. That's why you end up with. And then tangent is Y over R, but Y is negative. Even though X is positive, this will give you a negative result. So this is the signs of your trig ratios by quadrants. So always remember that. In the first quadrant, all your trig ratios are positive. Second quadrant, only sign is positive. Third quadrant, only tangent is positive. And then fourth quadrant, only cosine is positive. This also applies to their reciprocals. What are their reciprocals? We go back quickly. We talk about the cosec, sec, as well as cot. So if you happen to find that in the fourth quadrant, the cosec is positive, it simply means even the secant, which is the reciprocal to this cosec, is also positive. If you go to the third quadrant and say, let's look at sign in the third quadrant, and then happen that sign is negative, it simply means even the reciprocal of sign, which is the cosecant, will also be negative. So that is what you will always need to remember. Then there is this famous abbreviation. I don't know, it's up to you how you look at it, but please always remember this. This is actually your ticket to this, because you'll end up messing up the signs. But once you grasp this or understand this diagram here, or these letters, meaning of them, you will always conquer this thing. So in the first quadrant, that A indicates that all your trig ratios are positive. And then in second quadrant, it indicates its sign that has the positive sign, the rest, they are negative. So it's a sign and it's reciprocal, always remember that. And then going to the third quadrant, the tan is the one that is positive. Go back, you see tan is positive there. And then fourth quadrant, it's the cosine that is positive, of course, with its reciprocal. So please by heart this diagram. This will help you a lot. So let's look at the example. Suppose now you have this equation. You have 3 tan theta minus 4 equal to 0. Now the theta is restricted between 180 degrees and 360. So let me go back and look at this diagram. This diagram, I indicated angles. Here, when you start from here, you'll have 0 or 360. So if you go up here, vertical line, you'll have 90 degrees. That will form a right angle triangle if you construct a triangle. Then you move again 90 degrees unit, or 90 degrees to the horizontal line, which is going to be 180 degrees there. And then once you move 90 degrees again to the 270 degrees, and also add another 90 degrees to go back to 0, which is same as 360. So this will help you to actually locate. First of all, you'll have to understand that in the first quadrant, which is what I've just mentioned, all the trig ratios are positive, and then second quadrant sine and its reciprocal, then third quadrant tan and its reciprocal, and then fourth quadrant cosine and its reciprocal. So once you know these angles, that will help you to actually evaluate or respond to the questions like this, and it will actually make your life much simpler and understand that all these things are done in a Cartesian plane, which is a beautiful thing. So let's look at this problem, then let's solve it using a diagram. So we are given this information, and that information, that theta lies between 180 and 360. So what we want to find what will be the value of 25 sine squared theta minus cos theta. So using a diagram, first of all, let's use the information that presented to. We have tan of an angle theta. Remember, tan is defined as y over x. That's fine. So here, we can come up with tan. So in other words, this can be, if I can just put it like this can be written as tan theta equals to 4. Then we divide by 3, which means it's going to be the tan theta equal to 4 over 3. So we just transpose 4 to the other side, and then we divide by 3. So basically, we know that tan theta value is going to be 4 over 3. And then going back to the definition of tan now, tan is actually y over x. So we do have that information. And then now we are given that this case tan is given by 4 over 3. This simply means, first of all, tan gives you a positive result. So we'll have a positive here. This is positive. So this value is positive. It's 4 over 3. And then we know the definition of tan is that. But how does this help us? Because we need to draw a diagram and locate this a point and form a right angle triangle such that we can actually use probably a Pythagoras theorem to solve the problem. Why do we think we will need all that diagram and information about how to use Pythagoras? We'll have a sine. Sine is defined as, in this problem, we have sine. Also we have cosine. So in other words, we'll need to have adjacent side, which we know in this case is going to be, but first of all, we need to locate exactly where is the point. So that will help. So let's draw the diagram first. Well, let's try to draw a simple diagram here. So ask yourself, where can I locate this point? You have that information. You have this, and then theta is between 180 degrees and 360. So theta is somewhere between here and here. And then how do you tell that theta will lie on the third or fourth quadrant? It's because the value of this one should be the one that is guiding you. So you get a positive value here. It means we cannot locate our theta to be in our fourth quadrant, simply because tan there it's always negative. So tan will be positive in our third quadrant. So if we draw this line like this, so we construct a right angled triangle like. But first of all, what you need to note here, the third quadrant, both x and y are negative, but we have a positive result. That's interesting. But what we will do is that we should have 3 units from 0 to the left, and then you should have 4 units going down. That's your y, and that is x. Hope that is clear. So this will be -4 instead of just 4, because they are just both positive. So let me write it clear so that you can see that's a -4. So you have a -4 there. So because we're talking about distances, distance from 0 from here to here is 3 units. And the distance from here to this point here, or this value here, which is -4, is actually 4 units. So we know our x and we know our y based on this. So what is really missing is actually our r. It is very, very simple to find that, because of this famous theorem that tells us the relationship between this hypotenuse and the square of the other two sides. So we have this theorem that will help us to find R. So we can quickly find R. So that means we'll have to replace where we see X, we can put -3. And then where we see Y, we can quickly put -4. This is equals to 9, of course. There's a square there. So if we square this, it's going to be 16. Then we add 16 to 9, it should give us 25. And then this is R squared, it's not R. This simply means our R, or radius now, which is supposed to be positive, it's going to be 5. Even though the R squared, if you put a square root on both sides, should give you plus minus, we will consider plus because we're looking at radius. So this is our radius. But this simply means we should be able to see or to find the value of this, because now we do have all these information that we need. We do have R, we do have Y, we do have X as well. So how do you find this one? Let's first talk about sign before we even put it in together to solve the problem. What would be our sign here? Sign is defined as Y over R. What is our Y? Our Y in this case is -4 all over. What is our R? We just found R, which is that. This is the value of sine. If I'm ambitious, actually, I'll go on and check cosine. Of course, cosine I need it in this case, and then tangent, or tangent is given as well, and other the reciprocals of this. But then let's look at what we need specifically for this problem. We'll need cosine. We will need cosine. So we want cosine theta, which is defined as x over r. Our x, in this case, is going to be this value. From here to here, that's going to be our x. Our x value is -3. Remember, our r is 5. So that's what we need. From there, the problem is almost solved. But we can write it here because we want 25 sine squared theta -5 cos theta. This will be equals to 25, of course. And then we have to replace sine theta. We know sine theta is actually -4. We just found it here. Going to be -4 over 5. But it's squared, so it should have square. We are squaring this value. And then -5, we have to, where we see cosine, we can put -3 over 5. The problem is almost solved. It's just arithmetic. Now you can simplify, because it's going to be 25 multiplied by, which is that, it's going to be 16 over 25. Well, squaring this thing inside the bracket, I'll get 16, then I'll get 25 in the denominator, minus, I have a 5 there. So I can simply say this 5 will cancel that 5. And then I have a negative sign, and a negative sign, this will give me the positive sign, which is 3. So again, this will happen, this will cancel that, and then I'll end up adding 3, which will give me 1, 9. So that's the example. So now moving to the next one, the next section will be about reduction. So what do we do here? what we intend to do is actually expressing a trig ratio of a non-acute angle in terms of a ratio of an acute angle. Because, of course, we believe it's easier to work with the acute angles. What are acute angles? Those are angles between 0 and 90. So those are the angles in the first quadrant. Let me quickly go back here. So acute angles will be found in this quadrant. Once you hit 90, that means you should have a right angle. If you construct a triangle there, you should have a right angle there. So you go to second quadrant, I think we'll have obtuse angles. But anyway, how do you actually deal with angles that are greater than 90 degrees? It's very, very, very simple. You'll have to think of your Cartesian plane. You have 90 degrees. Let's start with this. I always refer to this picture. So please remember this picture. You start from 0 and you go to 90 degrees. Add another 90 degrees, you go to 180. Go to from 180 to 270. From 270, you add another 90, you go to 36. So now we want to see how would we write, how would we end up writing angles, or how would we write ratios of non-acute angles in terms of ratios of acute angles. So we will end up actually referring to these points, or these angles, I should say. 180 degrees, you go all the way to 360. So remember this sketch. Let's quickly go to reduction. How would you write 150 in terms of an acute angle, any angle that is between 0 and 90? So you can simply think of, I can write this as 180 minus, and if I like, I can show it by diagram and say, this is my diagram. I know I have 180 here, right? This is 0. This is 90. So I know this angle, which is 180, an angle that lies somewhere here, or in the second quadrant in a way. So I'll have it here. It's something like that. But if I know that once you hit this horizontal line, which is that, I'll have 180. But I know this angle, if we go all the way and go to this line, I'll have 150. I can just say, I will have 180 degrees, which is the full angle from this line coming all the way to the same line, now the horizontal line. Only have to subtract this portion of 30 degrees. That's all you need. As simple as that. As simple as that. So that means now I can write this as, just say I have a cosine. I'll have a cosine of 180 degrees minus 30 degrees. That's same as saying cos 150. So even if you look at 210, 210 lies on the second quadrant, somewhere here. Why can't I say I have 210? Can I add something to 180 to get 210? Of course, you can add that 30 degrees. Now we are moving to the third quadrant. So I'm on the third quadrant. So you can write this as tangent of 180 degrees plus 30 degrees. That will also give you tan 210. And then look at sine 330. 330 is in the fourth quadrant. So how can you just write that in terms of an acute angle? That's very simple. Think of 360 because now you are somewhere here. You have 360, so you can write this as sine of 360 degrees minus something. What is that something? It has to be 80 degrees. And then this will give you 330. And then How about the cosine 200? 200 degrees lies on the third quadrant. So we can write this as cos into 180 degrees, and then we should add something. We can add 20. That will always give you 200. So it's very simple. You can actually figure out, because we just look at 180 or 360. We'll also look at how do we deal with those that relates to 90 and 70. I just pushed that to the last topic, because that involves co-functions most of the time. So let's just gather this one first. So it means this one can be written as sine into 180 degrees minus some angle, which can be 50 degrees lies on the first quadrant. So let's make sure that that angle lies on the first quadrant. That's an acute one. And then lastly, let's look at tan 320 degrees. Again, this angle lies on the fourth quadrant. You can think of 360. So you can have tan of 360 degrees, 360 degrees minus some portion, which is 40 degrees acute. So it's very, very, very simple to write it in that way. So I just put a sketch next, just to show you that we have acute angles here. Those are the angles between 0 and 90. Then second quadrant, you can use 180 minus. So 180 minus some angle. Then in the third quadrant, you can have 180 plus some angle. And then in the fourth quadrant, you can have 360 minus. So there's more examples that I want to share as well. So, but what I'm interested in here, as we're going to look at this sine 180 minus, it's actually the signs now, combination of the signs. How are we going to actually look at the signs? Maybe I should mention this before I move to that writing it this way, or writing this in terms of an acute angle, it simply means you can always write a trig ratio only in terms of an acute. So maybe I should also bring that to your attention. Let's just write this last part before we move to that one, so that we can understand the next part easily. So how do you write this one now? It simply means you look at the quadrant. Let's pay attention to that. Let's think about quadrants. You have 180 minus 30 degrees. So that means it's an angle that lies in the second quadrant. Think about sides. Let me use a different color when I refer to sides. What would be the sign of cosine? Is it going to be positive or negative? We find that in the second quadrant, only sine and its reciprocal is positive. It means I'll always have a negative cosine. So that can be written as just negative cos of that acute angle at that point. So same thing transpired to this next one, which you can think of the tangent now, 180 degrees plus. That would be the third quadrant. And there is always positive. So we can have plus the tangent of that acute angle, which is this. You can do it for the next one. Think of sine 360 minus 30 degrees. That is in the fourth quadrant. Only cosine and its reciprocal positive there. It simply means sine has to be negative, or we'll have a negative sign there. So we'll have negative sine of 30 degrees. So you can write it like this actually, which is very, very nice. Now it's very simple. It is in terms of an acute angle. We don't have that angles that are greater than the big angles. So we can carry on, maybe finish this 3 quickly. Look at cosine. Now we're looking at cosine 180 degrees. This means we are in the actual on third quadrant, where cosine is negative. Only tangent and its reciprocal are positive. So here in this case, we'll have a negative cosine of 20 degrees. And then moving to the next one, think about the sine first, because if you forget the sine, you get the wrong answer. Think about the sine of sine in the second quadrant, that is 180 minus. What is the sign there? It's always positive. So you'll know that it's plus. I just put in plus so that you always remember that you think about the sign first. If there's plus, you can always leave it. But it's very, very crucial to remember that. So plus, sign is always positive in the second quadrant, and then you'll have sine. This is equal to sine 50 degrees. And then lastly, think about the tan in the fourth quadrant. Only cosine and its reciprocal are positive. So we'll actually have the negative value for the tangent. We'll have the negative tangent of 40 degrees. So please put that in mind. That is how we can write it as that. And then that means you can always write this in that way. So let's look at this one now. How would you write 180 degrees? Now as a single, in terms of just theta, it's very simple. But you'll have to pay attention to the quadrant. You have 180 degrees minus theta. That means you are referring to the second quadrant. So you are talking about this angle should be in the second quadrant. So you put the sign first so that you don't forget. Plus, sign is always positive in the second quadrant. And then you'll have the sign of the angle, which is theta, which is. So that is how you can write it. And then moving to the cosine as well, 180 minus. Only sine and its reciprocal are actually positive there. It simply means what you'll have for sine is negative. And then we'll end up having sine. It's actually cosine now. It's cosine theta. And then moving to the tangent one, we'll have -1 as well, because we're still in the second quadrant. So we'll have a negative tangent. So we'll do the same as you go to 180 plus. 180 plus will take you to the third quadrant, where only tan and its reciprocal, which is cotangent, are positive. The rest are negative. So I'll know exactly that for sine, I'll have negative. And then when you go to the cosine as well, the cosine is always negative in the second quadrant, only positive in the fourth quadrant. And then this guy now, which is tan and its reciprocal, that's the one that is always positive. So simply means this can be written as sine, and then this can be written as cos theta, and this is tan theta. So here we must pay attention to the quadrant so that we get all these signs correct. And then the third one, the fourth one, I mean, that's the fourth quadrant. Maybe I should indicate and say here it's 180 minus, so this is going to be our second. And then this one has to be our third quadrant. Obviously, the last one will be fourth quadrant. One will be asking why don't you look at the first quadrant? When you're looking at the first quadrant, all these that will be positive. But anyway, we'll look at that later. So let's look at 360 minus. Remember, in the fourth quadrant, only cosine and its reciprocal, cosecant, only those two are positive. The rest are negative. So that simply means if I see sine, just put negative, and then I know exactly what to do. And then if I see cosine now, I'll put plus. If I see tan, put negative. So now the sine is negative, then it's going to be sine theta. And then the cosine is positive, it's going to be cosine theta. And then the cotangent is negative in the fourth quadrant, it's going to be negative tan theta. That's the signs and how you can write it simpler. So in the first quadrant of acute angles, that's what we need to also visit as well. So, but before that, I want to look at some few examples. How do you simplify if you have situations like that? And then we have 180 degrees plus. Think about the quadrant. I'll use this purple card for the sign. So 180 degrees in the third quadrant. Is the sign negative or positive? Sign is negative. So you will have your sign. And then now, let's look at the denominator. Sine of 180 degrees minus, that's the second quadrant. The second quadrant, we have positive sine. We're gonna have sine theta. So this simply equals to just -1. So moving to the next example, which is the cos of 180 degrees plus x multiplied by tan of 360 degrees minus x. I just use x, just change it. You can always use any angle of your preference. As long as you understand that you're adding this to 180, that means we'll take you to the second, the third quadrant, I mean. So we have 180 degrees plus x, take you to the third quadrant, and tan of 360 minus x. This will be in the fourth quadrant. And you have tan 180 minus x, that would be the second quadrant. So how do you simplify that? You want to write it as, want to express this as simple as possible. So let's look at this portion first, the cos of 180 degrees. How would you write this in simple form? Remember, this is actually the fourth quadrant, and the sign of cosine is actually negative. Let me just write that negative. And then you'll have the cosine x. So that's the first part, cos of 180 degrees plus x. Then the next thing is, this is multiplied by the tan of 360. Remember, tan in the quadrant is actually negative. So again, you will have to have negative tan x. So I'm done with the numerator, then I'm moving to the denominator. And then the denominator is actually just tan of 180 degrees. 180 degrees minus x, remember that is your second quadrant. And then what is the sign of tan there? It's actually negative. So we'll end up having negative of tan x. So simply means now, if we were to look at this, you have a negative tan then that, or that would cancel off. So we'll end up having minus cos x. That would be your result. That has been simplified. So that is how you can look at it in terms of simplifying this kind of problem and so on. Let's look at the last one before we move to the next topic. This one includes a square. It has squared. So how do you deal with that? Very simple. It's basically have to write this, because what you need to remember is that this is like you are squaring whatever you have square. So it's whatever that you can have, and then you can square it. You are squaring that ratio basically. And then whatever that we have done, changing of writing this in simpler form can also be applied. So let's just look at it. How would you write this one? I'm using a different angle as well. You can use theta, x, it depends, it doesn't matter. You just use whatever you prefer, or use whatever you're given in terms of the problem you're solving. So, but that indicates the angle. So that's 180 degrees, but plus a portion, which is that theta.
Mkhize,
Yes,
yes. I'll give you just 1 minute to round up.
Oh, sorry, I haven't looked at time. Seems like I won't finish. But let me go quickly. Okay, 1 minute.
Okay.
Let me just finish this problem. Then, Mr. Dubazan, seems like I won't finish all the problem.
Okay.
And then this one will be the cos. And then remember this. We're thinking about 180 degrees plus. So that means we are looking at the third quadrant. So this is a square. So pay attention to a square, that you square something, you'll always have something positive. So basically you'll end up with cos squared multiplied by, and then look at the other one, it's going to be sine squared alpha divided by the sine alpha, which is 180 minus. So 180 minus sine is positive, but we have that that square over there. So if you look at that one, we have a square there as well. Look at that one, we can also look at cosine, and in the first quadrant, what is cosine in first quadrant? That one will give us negative cos of alpha. So we can simplify that one. It's very simple. So obviously this cancel that and so on. Then we have this minus, it should have minus cos. If you simplify, you cancel all that one. So sorry to buzz, and I haven't looked at time. I think I'll stop here. Yeah.
Oh, okay. Thank you very much, Mr. Mkhize. That was a beautiful lesson. So if you have a question for Mr. Mkhize, you can either send the message on the chat box, then we'll answer you, or you just wait for his slides that he will send later. So at 12 we have a science show. So those who are doing grade 11, you can come back at 12, or just stay through towards the next lesson. So the person that will present next is Miss Phumla Sithole. She'll be presenting trigonometry for grade 12. So, okay, Mkhize, you can unshare and
share. I don't know what's happening. Okay, please.
Yeah. I think that's fine.
Good morning.
Good morning. How are you?
I'm okay, thanks. How are you?
I'm good. We're good. Can you please try to share your screen?
Okay, I'm going to be using the whiteboard. Okay.
Oh, okay. That's fine.
Okay. So I'm trying to sort it out. Okay. Please tell me when you can see it, that side.
Okay, we're still waiting for it.
Okay.
Okay, now it is loading.
Okay.
I think,
Okay.
yeah, I think you can see it. So let me
Okay,
just.
okay. So good morning, everyone. My name is Phumla Sithole. I will be taking you through grade 12 trigonometry. So I have prepared a number of questions that we will go through. So I'll start by proving the left-hand side with the right-hand side. So I would like to show you first the things that are very important when you are trying to solve these questions. So by now you should know your identities. So identities that you should know. So the first one is this simple one, cos squared x plus sine squared x is equal to 1. So it's the same as sine squared x plus cos squared x is equal to 1. So this one is very essential. And another one is when you have double angles, because you are going to be using those as well. So our double angles, so we'll start with sine 2x, which is, it has only one, the sine 2x, which is the same as 2 sine x cos x. Then the third one is the double angle for cos. So cos have three possible outcomes. So the first one is when you have cos squared x minus sine squared x. So you would, for you to find the other ones, you would have to derive them using the other identities. Then you would find 2 cos squared x minus 1. The other one is 1 minus 2 sine squared x. So when you are doing this, proving the left-hand side and the right-hand side, it's very essential to know this, because sometimes when you are trying to simplify, you find that you get something like this, where at some point you have to replace it with cos 2x. So yeah, so this is very essential. Okay, so let's move on. So, okay. May I please ask, do I have the second page, or should I remove this Dubazane or Njabulo?
Yes, I think maybe you can try at the bottom right.
Okay.
Yeah.
Okay, I think it is safe there. Yeah, let me remove this one. I'll do the same thing. Thank you. Okay, so now let's go ahead and solve the proving of the left-hand side with the right-hand side. Okay. So the first one that I'm going to be doing today, we have minus 2 sine squared x plus cos squared, oh sorry, it's cos x. Okay, let me remove that. Okay, cos x plus 1 divided by. So we have 1 minus cos, then brackets, we have 540 minus x is equal to, we are trying to show that it is the same as 2 cos x minus 1. Okay, the first thing that you should look for, when you are trying to solve these kinds of questions, you need to look at the side that is very complicated. It may happen that both sides need to be simplified, but start by the one which is a much simpler one. So our left-hand side is already simplified. There is nothing you can do on this one. So we now have to simplify the left-hand side. So let's go ahead and do that. So the left-hand side is equal to, so we have minus 2 sine squared x plus cos x plus 1 divided by 1 minus cos 540 minus x. So let's say you have a Cartesian plane. Here's your Cartesian plane. From here, when you have a revolution, you have 360. So in most cases, we are used to questions which has 180 maybe plus x, 360 plus something. Okay, let me say 360 minus x. So when you have 540, it's the same as 1 revolution, then you add a certain number to get to 540. So to simplify this one, you would have to make sure that you find the angle that is after the revolution. So let's see. Which number is that? So you would say 540 minus the first revolution, which is 360. Okay, you minus 360. Then you find that it's 180. So we are used to 180. So it's not a big deal. So now I can write this as minus. Okay, another thing. Earlier, I did show you the identities. So since I am finding myself getting sine squared theta, I can derive the other one, the cos squared theta plus sine squared theta is equal to 1, and make sine squared to be the subject of the formula. So now I replace it with 1 minus cos squared x plus cos x plus 1. Okay. Why did I do that? It's because my right-hand side is guiding me that I have to simplify it. And the linear term, which has 1 as the exponent, is cos. If I had sine, I would have kept the sine. Yeah, so that's how you see you need to change. So you have to have everything in terms of one trig ratio. So in this case, we have cos x. So that's why I changed this from sine squared x and replaced it with 1 minus cos squared x. Yeah. Then let's go ahead. You have 1 minus cos. So you can include this part where you still have the 540. So you'll have 540 minus 360 minus x, right? So then after that, we can just simplify this. We have minus 2 times 1, which is minus 2. Minus 2 times minus cos squared x. So in this case, we'll have a plus because we're multiplying negative and negative. Cos plus 2 cos squared x plus cos x plus 1. Okay, then divided by. So the denominator, we did show that 540 minus 360 is equal to 180. So I can just replace that with cos 180 minus x. Yeah. So now, since we are here now, we need to simplify. So this one, you have cos 180 minus x. So that is in the second quadrant. And cos in that quadrant is negative. So you have to replace it with minus cos. So another thing that is very important, when you are replacing, make sure that you use brackets. because if you don't use brackets, it may seem like you are minusing. I'll show you what I mean. So let me rearrange this. I have 2 cos squared x plus cos x. I do have like terms minus 2 and 1. So I'll end up with -1. Then you divide it by. Okay, my denominator, I said this is in the second quadrant, but we are simplifying it. So I'll have 1 minus, then put a bracket so that I can show that it's in the second quadrant. So it's going to be minus cos x. Then the next step will include me having a positive one because I have plus here. So now I have, okay, let me just simplify everything. So I find myself having a trinomial, but in terms of trig ratios, cos x. Okay, so what I mean by that, I find myself having, move this. Okay, let me write this first as it is. Cos squared x plus cos x minus 1 divided by. Now I have 1 plus cos x. Okay, so now I find myself having a trinomial. It means once you see a trinomial, it means you need to factorize. So that's what I'm going to do now. So I have 2 cos squared x plus cos x minus 1. So your first bracket will have a 2 cos x. The second bracket will have a cos x. So since I have a 2 here and my middle term is plus 1, I'll have to have a term that it will be here have a positive because it affects the middle term. So I'll have a 1 here that is positive, and here I'll have a minus 1. So these are the factors that we get divided by. Okay, so now you can also write the denominator as cos x plus 1. This is the same thing. Since you have positive and positive, you can write it like that. So as you can see now, we find ourselves having the same factors. So my factors for the numerator are these two. Then this one is the same as the one that is in the denominator. So they now can cancel out. Then you are left with 2 cos x minus 1. So this is how you would solve a problem that is like that one. So we have found the right-hand side. So you can conclude the left-hand side is equal to the right-hand side. Yeah. So it makes it easier when you do know the identities. They are very crucial. So please make sure that you know your identities. Okay, let me go ahead and have the next question. So for the next question, we are trying to simplify as well. Okay, so for the one that we have here, please pay attention how I use the identities that I introduced earlier. So I showed you for a double angle for cos, I showed you a double angle for sine. So we will be doing that here. We will be using those identities. Okay. Okay, let me have them on the side just to remind myself. Okay, so the first one is sine 2x, which is the same as 2 sine x cos x. Then the second one is the cos one, cos 2x, which is the same as cos squared x minus sine squared x. Then the next one is 1 minus 2 sine squared x. The third one is 2 cos squared x. Okay, so now I'm going to be writing my question for this one. Okay, so we have sine squared 35 degrees minus sine squared 35 degrees divided by 4 sine (10 degrees cos 10 degrees). Okay, so when you here we're supposed to simplify this. So when you have something like this, so the first thing in your numerator and your denominator, you need to look at the angles that you are given. In this case, for the numerator, we are given 35 for both. Okay, no, this one should be, sorry, should be cos. Yeah, sorry about that. So you need to look at your angles, then you can go ahead. So these double angles, they work when your angles are the same. Bear that in mind. So we have sine x here and cos x. So here you have to look if you have the same angles. So we do have the same angles for the numerator and the denominator as well. We have the same angles. So this one, it seems to look like the cos 2x, but here the sign is positive and the cos is negative. In the double angle for cos squared is positive and sign is negative. So you need to make means to achieve what you are given as the double angle. So how would you make those means? You can take out the negative from the numerator. So the numerator, you can write it as minus, then bracket. Okay, so when you take out the numerator, you can take this out and start with this one. So you're going to have cos squared 35 degrees. Then when you take out a negative here, this sign now will be negative. So you can write it here. So you'll have sine squared 35. So bear in mind, we still have the same angles. So you have to divide by. Now we are seeing that for the denominator, we find ourselves having something similar to the double angle for sine. Let's check if our angles are the same. Yes, we do have the angles that are the same. Then these two angles is 10 degrees and 10 degrees, they are the same. And this one looks like 2 sine x cos x. So what I can do for the numerator, I can split this 4. I can write it as 2 times 2. Then I have sine 10 degrees cos 10 degrees, right? Then this one, it looks like sine 2x. So in this case, our x is 10 degrees. So what I can do, I can just say 2. I'll start from the back, like from the right hand side. I have 2 sine 10 degrees cos 10 degrees. So if I were to write it in this form, it would be equals to sine 2, then brackets, our angle here is 10 degrees. So I can go ahead and replace this one, this part, by sine 210. Okay, so let me do that. So the numerator, I find myself having a cos 2x. So I can just replace it, cos 2x divided by, then since I am replacing it with sine 210 degrees, 2 times 10 degrees. So I am going to end up with minus cos 2x. Okay, sorry, now I wrote theta instead of 35. So this would be 35. Okay, even here, it's supposed to be 35. So I'll just multiply it. So it's going to be 70 degrees divided by. So now we have 2. Then sine 2 times 10 is sine 20 degrees. Okay. So when you find yourself having the angles which are not 90, 180 and special angles, you need to make means to simplify it. In this case, it looks like we need to simplify the numerator because the smallest, you can simplify the denominator as well, but I'm choosing to simplify using 70 degrees. So when I do that, I can just apply reduction. I can say that 90 minus 20, it will give me 70 degrees. So this is the first quadrant. So everything is in this first quadrant. As we know that when you are using the reduction and you find yourself having a 90 degrees as the angle that is here, you are going to use the reciprocal, which is cos, which is sine in this case. The reciprocal of cos is sine. So we are dealing with the first quadrant. So everything in the first quadrant is positive. So there won't be a sign change. And the sign that you use is usually for the original, not the one you are changing to. It's for the original. So it's minus, then I'll have a sign 20 degrees. So I have applied reduction here, divided by 2, 20, or sine 20 degrees. So I find myself having the same thing. I divide both sides by sine, yeah, because they are the same thing. Then I find myself having the answer, which is negative 1/2. Okay. Yeah, that's how you would do such a question. Okay, let me move on and do the next one. Okay, so I have found the next page. So now I'm solving for sine 140 degrees, sine 360 minus x divided by cos 50 degrees tan of minus x. So we are asked to simplify. So let's simplify this one. So the first thing that you must know is that when you have sine of a negative x, your answer will be negative sine x. When you have cos of a negative x, your answer is positive cos x. Then when you have tan of negative x, it becomes negative tan x. The only thing that remains positive is this one, the cos one. So that is very important to note. So now let's go ahead and simplify. So we find ourselves having 140. 140 is not a special angle. We need to make means if you are not getting a special angle, at least it has to be the same as the other angle in that problem that you're trying to solve. So in this case, we do have a 50 degrees. So we can make means to get a 50 in the 140. So we can say 140 is equal to 90 plus 50. Yeah. So we can change that. So we have sine 90 plus, okay, 50. Then we have sine. This one we can just simplify it. This is the fourth quadrant. So sine in the fourth quadrant is negative. So let's go ahead and replace it with the negative. It's going to be minus sine x. So if you make a mistake of leaving the brackets, it may look like you were it may look like you are subtracting here. So make sure that you include the brackets so that you can show that you are multiplying. Okay, then in our denominator, we have, you may leave the cos 50 as it is. Okay, so the tan, as I showed you here, it's going to be minus tan x. Then we go ahead and simplify. So since now we find ourselves having sine 90 plus 50, since we have the 90, it's going to change to cos, but in this case, we are going to take the sign of this sign, not the cos we are changing to. It's going to remain positive because 140 is in the second quadrant. Yes, sine in the second quadrant is positive. So I'll have positive cos 50 degrees. Then I'll go ahead and have the minus sign. So I have this because I want to show you how it works. Divided by cos 50. Then you can just, they can cancel out the sign, the negative, they are divided. So we end up with something that is positive. That's what we can do as well. So let me just remove it. Now I have tan. So we find ourselves having the same thing in the numerator and the denominator. So you just cancel them out. Now we have sine x divided by tan x. So what you need to do, by now you know that tan x is the same as sine x over cos x. So when you find yourself having to divide by a fraction, what you can do, just write the sign that is in the numerator as it is, then divide using the divide sign, the fraction. Then your answer now, when you have fraction, you do know when you are changing from divide, it becomes multiply. Then you flip what was in your numerator, it goes to your denominator, vice versa. So now you'll have cos x over sine x, then they cancel out. You'll be left with cos x. Yeah. So that's how you solve such a question. Okay. Let's go ahead and do the next one. Okay, in this case, let's say they said they gave you sine 36 degrees. Is equal to square roots of 1 minus p squared. So the first thing you need to note is that if you were to include a diagram, this will be in the first quadrant. So in the first quadrant, what you need to note, everything is positive. Your x is positive, your y is positive. So these types of question, when you are given something like this, the first thing that you need to note is that you need to put the ratio that you're given in terms of x, y, and r. In this case, we have sign, and you can write it as a fraction as well. So if you're writing it as a fraction, you can just divide it by 1. So now we do know that sine, I'll just include it here, sine theta, let's say it's sine theta. So in this case, it's 36. So I'm just showing you it's y over r, and cos theta is x over r, and tan theta is y over x. So this is very important. You need to know this. So in this case, we have sine 36 degrees. Since it's 36 degrees, it's in the first quadrant. So whatever we'll be working with is going to be positive. So this is y over r. In this case, y is equal to this one, and r is equal to 1. So the following questions, maybe they say tan, you need to find tan 36. You also need to find cos 108 degrees. So in this case, we do have two like units or variables, y and r. X is missing because the ratios include x, y, and r. So you need to find the x that is missing. So you need to use the Pythagoras theorem always when you are trying to find the missing variable. So this is your Pythagoras theorem. In this case, we have y, so we're looking for x plus. So we replace y with 1 minus p squared, then square k. There's a bracket here, and a square root is equal to 1 in this case is, r is 1 in this case. So then you go ahead and simplify. So you need to be careful of the algebra. So when you are squaring a square root, it just disappears. Then you plus by 1 minus p squared is equal to 1. Then you solve for x. You take everything to the right. You have 1 minus 1 plus p squared. Okay, so these two, they will cancel out. Then you have x squared p squared. Okay, when you are in this form, usually you say x squared. Okay, now you're trying to solve for x. So usually you say x is equal to plus or minus square root of p squared. Since I had mentioned earlier that you are in the first quadrant, so everything is expected to be positive. That's where you remove the negative. So we are choosing a positive x value because we are in the first quadrant. Okay, so now since we have found the x value, now we need to go ahead and solve for tan 36 and cos 108. Okay, let me remove this. So tan 36, in this case, it would be y over x. So we have tan y over x. Even for this one, it applies the thing of checking your angles that you are given. So in this case, we can go ahead because we were given sine 36. So it's safe to go ahead. So because now we are also trying to find 36 degrees, tan 36. So in this case, we do have y, which is square root of 1 minus p squared divided by. Then the x in this case is the one that we worked out. Okay, I didn't simplify it. It's equals to p. Then we have p as the answer. Okay, then for the second one, we find ourselves having cos 108. Okay, so in this case, since we have cos 108, since we start by checking the angles that we given, 36 and 108, they have no relationship, but you need to make means to make them relate to each other. So what I can do, I can just say, use the reduction, 180 minus 72 degrees is equal to the same thing. Okay, I need to include the ratio cos. Sorry about that. So it's cos 180 minus 72 degrees. It is 108. So we can use the reduction, which this is the second quadrant. Cos in the second quadrant is negative. So you're going to have minus cos 72 degrees. So now, now I am seeing that 72, if you multiply 36 times 2, it is 72. So I can change this to 2 times 36. Okay, so we find ourselves having a situation of a double angle. So since we have a double angle, it's up to you. You can choose any of these to find your answer. So I'm choosing, let me choose the one that has, okay, in this case, minus. Then I replace it with the one where it's 2 cos squared theta. Theta in this case is 36 degrees minus 1. This is one of the double angles for cos, cos ratios. Then I can simplify this. It's equal to minus 2. Now I can replace the cos 36. Okay, when you have something like this, it is the same as so it's the same thing. So now I can just have a bracket. So cos is x over r in this case. So our x, we found s to be p over r. R is 1, so it's not as complicated. So you square it, then minus this one times this minus 1 is plus. So you would have just minus 2 cos squared 36 plus 1. Then you move along to the next step where you are now simplifying and substituting. Okay, now let's simplify. We have minus 2, then p squared plus 1. You can leave it like this, or you can rearrange it, have the positive first and have the negative at last. Then you have minus, it's 1 minus 2p squared. Yeah, so this is how you would do this one. Okay, so the other question I'm going to cover today, they say if you are given something like cos, okay, sorry. So you have cos 26 degrees is equal to m. Then they say find 2 sine squared 77 degrees. So this is a very complicated one where you need to use double angles, whatever you can use. So I'll start by introducing what I'm using in terms of theta, then I would replace it with the 26 degrees. So in this case, there's no way that you can make 26 and 77 to be immediately the same or they have a relationship. So what I'll show you now, let's go ahead and we have cos 2 theta is equal to 1 minus 2 sine squared theta. So this is a double angle for cos, the one that have sine squared. So it would be easier to use this one because we are looking for this problem. We're trying to find this. So it would be easy to find it using this one. So let me go ahead and in this case, I can just replace the theta with the 26, yes. Or not 26, sorry, 77, because I'm looking for 2 sine squared 77. So I need to replace it with that. So even here, I'll do the same thing. Then I multiply here by 77. Okay, so I'm taking this from the double angle for cos, and I'm using this one because I'm trying to find 2 sine squared 77 degrees. Okay, I can go ahead and make 2 sine squared 77 degrees that I'm looking for the subjects of the formula. So what I can say, I can take this minus 2, all of this to the left and take this one to the right. So they change places, like they trade. So I'll have 2 sine squared 77 degrees is equal to, now I have 1 minus, take this one to the other side, it's cos, I can say 2 times 77, it's 154 degrees. Okay, now since I find myself having this, so what I can do now is to simplify, because this one is what I'm looking for. There's no need to simplify the left-hand side. I need to try and simplify the right-hand side. So what I can do, cos, I can write the 154 as using the reduction. It's 180 minus 26. 180 minus 26 will give me the 154. And you see now the 26 that I have as my cos 26 is appearing. So now you can just use the reduction. So this is the second quadrant where we'll have a negative cos. So we have 1 minus cos of 1 or 26. Okay, sorry, let me. Okay, let me have the brackets. This is the second quadrant, so I'll have minus cos 26 degrees, which is the same as 1 plus cos 26. So earlier they did tell me that cos 26 is equal to m. So you just go ahead and replace it with m. So this is the answer for when you are trying to find sine squared 77 degrees. Okay. So I think I can end here for today. Siyabonga.
Oh yes, you were muted, but now we can hear you.
Oh, I'm ending here.
Oh, you're ending here.
Yes, because it will run out of time when I do the other ones.
Oh, okay. Thank you
Can
very
I
much.
Can I squeeze one, or I should end here?
You can squeeze one.
Okay. Okay, so, okay, thank you. Okay, so let me just have something. So I'm trying to do the compound angles. So you are given cos alpha minus beta is equal to cos alpha cos beta plus sine alpha sine beta. So this is a compound angle. So the question would be like, derive using this compound angle to find cos, derive cos plus beta.
Sorry, Phumla. I don't
Yebo.
think we see your screen currently.
Oh, okay. Let me
Oh, okay.
okay, you can see it.
Yeah, maybe others can testify if they can see what you are writing. Just try to
Okay.
continue.
Okay. So we are trying to derive for this one using what we are giving here. So in most cases, they tell us what the compound angles are, how they work. So, excuse me, when you have cos alpha minus beta, the way you expand it, you say cos alpha, cos beta plus sine alpha, sine beta. That's how you expand it. So now we are trying to derive this so that we can find something similar. So now what you do, you take cos alpha plus beta is equal to. Now what you need to do, you say cos, then you need to deal with this one. So you say alpha minus brackets minus beta. So these two are the same thing. So now what you do, you apply this format. So you say cos alpha, cos beta. Beta in this case is minus. So you have cos of minus beta. Then since we had a negative, here we also have a negative, you'll have a plus, this one, plus sine alpha sine minus beta. So you have a negative beta there. Then you simplify. So earlier I did mention when you have cos of a negative beta in this case, it's going to be positive beta, cos beta. So I'll have cos alpha cos beta. Then for sine, we have sine alpha. Then we have the plus sine alpha. Then this one, sine of negative beta, I'll have negative sine beta, which is equal to, so now I am simplifying cos alpha, cos beta. Then I take this negative and multiply with this one, I'll have a minus sine alpha sine beta. So I have derived what I wanted. Okay, let me do another one. So now we are trying to simplify. So let's say you have 2 cos 6x cos 4x minus cos 10x plus 2 sine squared x. Okay, so this one that I'm doing, we will be using compound angles a lot. So please pay attention. So what you do for the first one, we can just leave the first one for now and try to manipulate the other ones. So we have 2 cos 6x cos 4x minus. Now I have to split this, have 6x and 4x. Just so when you are splitting it, you don't multiply by it, you add. So you have 6x plus 4x. You are splitting it in these values because we are guided by the one that we already have here. So we have these two plus, since we have a square and we have x, it's giving us problems. So we need to make means to replace it. So what can we replace it with? We can use the double angle for cos. So the one that we were using earlier, 1 minus 2 cos squared x. So you can also use the, okay, in this case, yeah, it's not squared. It's supposed to be 2 cos. Okay. Erase. Okay, let me start by having it. Okay, I'll just write it here and I'll remove it so that we can see where it's coming from. So we have cos 2x is equal to 1 minus 2 sine squared x. Then I take this to the other side and the other one to the other one. 1 minus cos 2x is sine 2 sine squared x. So this is what I'm replacing this one with. So I end up having 1 minus cos 2x. Okay, I can remove this now. Okay, so now I need to simplify. Okay, I find myself having something like this. Let me simplify first, then we can go further. So we have cos 6x, cos 4x minus. Okay, let me leave this for now. 6x plus 4x plus 1 minus cos 2x. Okay, so we are aiming here for angles which are 6x and 4x. So I can also change the last term to be in terms of 6x and 4x. Minus. Okay, we have cos 6x plus 4x plus 1. Then I can change this angle to cos 6x minus 4x. Do you see everything now has angles 6x, 4x? Okay, now I can go ahead and have, okay, here I missed the 4. Now I need to use the expansion that I had earlier. So I'll just include a big bracket so I can show it's going to be cos 6x, the expansion for compound angles, cos 4x. Since I have a plus in between, it's going to have a minus. Then I have sine 6x, sine 4x. This one is for this one, this term. Then I have the one back. Then I do the same thing for the last one. So I have brackets again, big one. Then I expand using compound angles. It's cos 6x, cos 4x. Since I have a negative now here I'll have a plus. Cos, okay, it's going to be sine now. Sine 6x, sine 4x. Okay. Okay, now we can go ahead and just simplify. We have 2 cos 6x cos 4x. So we will find ourselves having like terms. So we need to add them, subtract where we need to subtract. So for this one, we have a negative, and these cos 6x cos 4x. So we have the same thing. These two are common factors. I'll just have a shortcut because we're running out of time. So these two, this one and this one are common factors. So I'll just say minus 2 cos 6x cos 4x. Then we do the same thing. Then you take this negative, you multiply by this negative, we'll get a positive. So this one would be plus sine 6x sine 4x. We've already taken care of this one, plus 1. Then we take this negative and multiply by this one, then it's minus sine 6x sine 4x. So these two are like terms, they will cancel each other. And these two as well are like terms, they will cancel each other. Then we are left with 1. So that's how you simplify such question. Thank you, Siyabonga.
All right. Thank you very much, Ms. Phumla. I don't think we have a question on the chat box. So thank you very much. Sneh, I will hand it to you. So I think now we should be having a science show.
Yes, thank you, Phumla. Our next presenter is Miss Ingrid Botha, who will be doing the science show. Hi, Ingrid.
Hi, good to see you.
Yeah,
All right.
good to see you. Yeah, I think you can start anytime you're ready.
Okay, fantastic. So let me just share my screen. Can everybody see my screen?
Yes, we can.
Okay, wonderful. So what I will be presenting today is a little bit on the experience in mechanical engineering at UKZN and the experience in mechanical engineering in industry. So I am a mechanical engineer, so I will be specifically talking about the mechanical side. However, in terms of how you will experience your life on campus, this can really cover most of the engineering fields. So that includes our civil, chemical, agricultural, electronic, electrical, and computer engineering fields as well. So thank you very much for having me today. So let's start off by just chatting a little bit about why do we study engineering. So first of all, it's to develop a critical understanding of the world around us. So if you're a student who, when you're on your drive on the way to school and you pass under a bridge and you wonder, how does this bridge operate? How was it designed? Or if you're playing with your phone or with your computer and you wonder, how does these things work? Then engineering might be for you. So it answers all of those questions. And it also allows us to generate a new perspective of problems and problem solving. And what I mean by that is it allows us to categorize problems and the methodology to solving it. And where this really comes in useful is in industry and in our work after we have finished our undergraduate. So in most cases, the reason why engineers have a very high employee rate is not only because of the technical skills that we gather at university, but also for this ability of problem solving. And that expands the career field for engineers into the finance industry, into management positions, and it allows us to work in a lot of fields outside of what you would traditionally consider as engineering. So over and above this, some of the other job opportunities that we can have or that we do, that you can go into is one being industry. So in that case, you'd be working for large companies such as SAPI or Sasol, for example. It allows you to do a lot of traveling all over the world. Then we have academia and research. So in this case, I'm an academic. I am lecturing here at the university, and I'm also completing my PhD research. So the reason why I went into academia was it allows you to work on a lot more diverse problems than industry. So in industry, of course, you're going to be limited to the products that you are busy developing. However, in academia and research, you can have a lot of control over the research that you are doing. And this is lots of fun because it means that every day you've got different problems to consider. If you're a grade 11 or 12 student and you're thinking, wow, when you want to work one day, you really can't visualize yourself as having a set 9 to 5 where you're kind of doing the same thing on repeat every day, then maybe a job in academia or research is for you, where it allows you to really have a diverse experience on a day-to-day basis. Then we have consulting. So consulting is not limited to only engineering fields. You can deal with a range of problems. A lot of the large accounting firms now have engineering consulting departments also included. Consulting allows you to do a lot of traveling as well as you deal with projects all over Africa and internationally. And then finally, you also have management positions. And as I mentioned, this is not just limited to engineering management positions. It can be, and where a lot of our undergraduates go is into the banking sector. We have most of the banks and the large finance firms come to the university and advertise positions specifically directed at engineers because of this ability to problem solve. And of course, definitely a motivation why quite a few people are studying engineering is, of course, it does have quite a large income bracket for engineers who are coming straight out of undergraduate compared to other career fields. So now that I've spoken a little bit about why you'd study engineering and why you'd become an engineer, I want to describe a little bit more about what it's like to actually study it over the course of the 4 years. So at UKZN, we have a 4-year program, and that includes honors in the undergraduate degree. So a typical day in first year would start off with going to your chemistry pracs. You get to don your white lab coat and your goggles. You get to go do some cool titrations. Then you'll probably head off to the physics lab to do physics pracs. And in first year, you have a lot of modules that you share across the engineering to kind of get a taste of all the areas and also to generate a good foundation. So lots of maths and physics. And I think this is something to emphasize that, especially if you are still maybe in grade 10 or grade 11, really, if you are considering engineering, really work hard on your maths and physics. Now, this is, of course, not only to get in or apply as an engineer and be accepted, but it's also going to help you a lot in first year. So that is where most of the students struggle, is grasping the maths and physics. So if you have a good foundation from high school, that's going to help you a lot when it comes to the first year of engineering. Then from the first year onwards, you start specializing more in your specific field of engineering. So of course, in mechanical, you do a lot more thermodynamics, fluids, design problems, design projects, and you get to learn how to use the equipment in our workshop. So you can see the workshop or an image of it in the top left-hand corner. You'll get to learn how to use specialized equipment like our laser cutters and our 3D printers. So you can see one of our 3D printers at work in our lab. You'll spend a lot of time in the lands, either doing homework or hanging out with friends. And then finally, the bottom right-hand corner is just an image of one of the common areas. And in between classes, you'll spend some time hanging out with friends, maybe playing a game of funny or two, and playing some pool. So now the question comes in is what other interesting projects do we work on in engineering? And one of the reasons why I do this presentation is to emphasize to high school students, especially those who do not know a lot about engineering or specifically mechanical engineering, that it's not all just about building cars or rockets, you know, and really being in a heavy factory type scenario every day when you're busy working. There is a lot of different design avenues when you're looking at where you can go from engineering. So some of those, of course, would be something like mechatronics, aeronautical engineering, aerospace engineering, biomedical engineering, soft robotics. So those are only a few, just thinking off the top of my head. And starting off, just showing you an idea of one of these projects. So in our final year, and I definitely think this is a highlight of the entire degree, is the final year project. So this forms the honors part of our degree, where in final year, you get to build an entire project from start to finish. You start at the beginning of the year and you need to have a completed constructed model that's completed testing at the end of the year. And it's all presented at an open day that's open to the public. And you get to present your ideas and designs to the public, which is really, really exciting. So in our case, that included a flying hovercraft design. So there you can see it in the process of being manufactured. I'll show some final images in a moment. And this is the kind of project that you would complete over the course of a single year. So it's lots of fun. You get to see your designs that's on paper really come to life in 3D. You get to purchase all of the components. We get a set budget from the department. And then just to add on to some of the other experiences as a student, it's not just limited to classes and what you can do within the modules. We also have student chapters. So we have the Engineers Without Borders student chapter, and this covers all engineering faculties. And you do a lot of outreach projects here. So this allows you to build your skills as you are working through the degree. And then we also have the SciMeki student chapter. So this is lots of fun. I've been involved with the SciMeki student chapter since I was an undergrad. It involves a lot of industry visits. We get to go see some of the sites. We get technical talks where we have professionals come in and tell us a little bit about their experience in industry. There's a mechanical engineering ball at the end of the year. Also lots of outreach projects. So one of those outreach projects is our Girl CAD course, which I'll talk about a little bit at the end of this session. And it definitely gives you an opportunity to see the potential of what your degree is going to become through these kind of experiences with industry. So here we have an image of the final hovercraft design. So just to give you an idea of why we built this, so the scope of this design was, it was required to be a search and rescue type vehicle that's able to operate in marshy terrain. So it's a multi-terrain vehicle. It can travel over hard ground and obstacles and water. So it's able to float on water. It can hover on the ground and you can drive it around. And you can direct it with the duct at the back. That's actually a small aircraft engine that we use. And when you encounter obstacles, the entire design is able to lift up into the air and glide over the obstacles using the two wings. So it was a really, really fun design. Lots of work, lots of late nights in that fourth year, but totally worth it to see the end result. So just to chat about some other notable designs that mechanical engineering has been part of. We have the solar cars that we've built. So in 2015, UKZN won the National Solar Car Challenge. And in 2016, the the solar car was shipped all the way to Australia to take part in the international championships. So there you can see an image of the solar car team all posing with the final design. Then we have the ASRI group, which is the Aerospace Research Institute. And one of their notable designs you can see is one of the rockets that they built. So they've actually just recently had another launch campaign, March this year. But the one that you see on the image, that was launched in 2021, and they managed to break the African altitude record for hybrid rockets. So quite a big achievement for them. They're aiming to break some more records with their future projects. And just in terms of what level these kind of designs are, these are postgraduate designs. So this involves our master's students and our PhD students. So if you're interested in going into research and academia, these are some of the cool projects that you can work on. But now the projects that I've shown you are really all large vehicle type projects, what you would imagine when you think of mechanical engineering. But I want to use my master's project and my PhD project as a stepping stone to be able to show you the diversity of studying mechanical engineering. So my master's research was dedicated to constructing a wearable Braille device. So you can see on the image, that's the 3D printed casing. So it's mounted on your hand. And what a lot of us who are not visually impaired take for granted every day, say, for example, reading a menu in a restaurant. Individuals who have visual impairments find that a real struggle. Now, what this device is attempting to do is it has a camera mounted on the device, and if they were to run their hand across any printed text, for example, a printed book or a menu, it immediately or in real time transcribes that text that's been scanned, and it converts it into a refreshable Braille dot system that's on the pad of the user's finger. So you can't quite see it inside the design, but you can see the type of actuators that I use. That's in the image to the left, to the right. And in order to achieve this design, very, very small actuators were required. So what we would commonly think of is linear actuators or motors that would be way too big to fit comfortably on a user's hand, especially because we wanted to target this for all age groups. So we ended up going with dielectric elastomers, which is a type of soft robotic technology where you have a very thin silicone or acrylic foam that's able to be flexible. You sandwich it between two electrodes, and when a voltage is applied to those two electrodes, it causes them to attract to each other and squeeze the acrylic foam in between them. And that causes that area increase that you see on the right. Now, in order to create the dot that actually buckles upwards, if you constrain the edges of that circle, it forces it to instead buckle upwards instead of expanding like you can see in that image. So this was a mechatronics project. I completed my master's in mechatronics, and it required me to integrate software and computer knowledge. So in that case, it was dealing with my microcontroller, which was a Raspberry Pi, being able to scan the text, writing code to translate that text into, first to recognize the text, then to translate it into voltage outputs. And those 6 voltage outputs would therefore actuate each of the dots. And you have to time it so that it's, to the reader, it would feel as if they are naturally running their hand across a Braille printed page. And just an interesting fact, the power or the voltage required to create these dielectric elastomers was up to 5,000 volts for one Braille dot. So for those of you who are doing physics at the moment, there's one reason how this can still be safe for the user, and that's because it has a very, very low current. So even if you were to touch this, it won't hurt you, even with something like 5,000 volts, because of the very, very low current. So that's just a nice real world example of the difference between voltage and current in the system. And then from this kind of design, you can see that there's more, you can see some more control systems and some more computational development coming in. And then we move on to my PhD research. So the topic of my PhD research was, or is, bio-inspired 4D printing. So that's quite a mouthful. So let me just break it down a little bit. So let's start off with 4D printing. So I'm sure a lot of you have heard of 3D printing, where you are able to create three-dimensional structures using a single printer. You can print it from either resins, powders, or plastics. And what we are aiming to do, and the dimension that we are aiming to add to generate a 4D structure, is to include the added dimension of time. So we want to, let's say, for example, the chair that you're sitting on. Imagine those chairs being manufactured and then having to be shipped to the person who purchased them. Now you can imagine that that takes up quite a bit of space in whatever truck or train or ship you're planning to transport them in. Now imagine if instead you would be able to print these chairs as a completely flat sheet. And once it's arrived at its destination, which is of course a lot easier to get to with it being in this shape, with the application of an external stimulus like heat or water or UV light, it will fold into its final shape. And that's without use of any specialized equipment. So that's what we're aiming to do with 4D printing. You can already see some of these structures in real world applications. So for example, they've now developed stents that you're able to inject into an artery. It moves to location, and then with the application of a stimulus, it can then expand into its final form as the stent. So this allows for non-invasive surgery. And then comes the question of, how do I include bio-inspired in this? So with the advent of 3D printers, it allows for a lot more unique design than what we've been able to do up to this point. So with traditional design manufacturing techniques, like using CNC machines and lathes, we've been very limited in the geometry that we could really manufacture. But now, with the addition of 3D printing, we can take inspiration from nature, and we can use this to be able to create optimized structures and optimized designs. So on the slide, you can just kind of see an idea of the workflow that I'm working towards. So it is quite an involved process. It covers a lot of different fields, where you've got the chemistry field, where you're actually synthesizing the polymer. You need to prepare it for extrusion. So these are composites. So you have to have an understanding of the different material properties before you synthesize. Then you characterize by running it through tests and experiments, and for example, investigating the structures using different microscopes. Then we get to the point where we create the architecture. And at the moment, the 3D printers that we have available, they create the final printing paths to allow you to print a structure. But this needs to be optimized to allow us to mimic natural forming bodies. So this is something that you'd have to generate with your own unique code in a program like Grasshopper. And then you get to the printing side, where you print your model and then finally investigate and experiment to assess the final success of the model itself. So just to give you guys an idea of how bio-inspired designs have been used, This is a structure that has been inspired by the hibiscus flower and the blooming of this hibiscus flower. So by mimicking this structure in an origami type pattern, NASA has been able to create something known as a star shade. So they send telescopes up into space to investigate planets surrounding distant stars. Now, the problem with this is the light from that distant star disrupts the investigation of those surrounding planets. So in order to block the light from that star to be able to inspect the planets, they use what is known as a star shade. And you can see that in the lowest row of this image. And you can see with the final shape of that star shade and the very large surface area that it has, it would be very difficult to try and deploy that into space to get it up there without being damaged and still be able to be operational. So by using biomimicry and bio-inspired design, you can furl up the design, so to speak, send it off into space, and once it's in position, it can unfurl and bloom just like a flower to achieve the final shape. So just to give an idea of this blooming mechanism that's involved, on the left, we can see the hibiscus flower and how it naturally blooms. And on the right, we can see the star shade in action. So this was just a simplified version of the star shade, just to show that unfurling motion that it's capable of. And that was inspired by biology. So here's just some other types of inspiration that we can get from plants. So some of you might be familiar with this. This is commonly known as the shy plant, the Mimosa pudica. It's often considered a weed in KZN, but it's got an amazing ability to, when you touch the plant, it's able to fold all of its leaves up as a protection mechanism. And very shortly after, it will unfurl back into its original position. And the way that it's able to do this is by the movement of auxins within the cells, and it creates one side of the stem, which is cells full of water, so they expand, and then the other side of the stem is cells that have very little water. So it causes it to move in a specific direction that's controlled by the auxin movement. And by using this design, we can then create specialized architectures or mesostructures that we can then apply in 3D printing technology. So other types of plants that we're currently observing is the lotus flower and the giant Amazon lily pads. So you can just see that beautiful venation structure, and that allows it to have that absolutely huge surface area on the water. So by observing this and understanding the mechanics behind it, we can start applying this into different engineered structures, whether that's architecture that we're going to see around us or mechanical structures. So that's pretty much sums up an idea of what you could possibly do with a mechanical engineering degree. I hope this has opened up the eyes to some students of the possibilities of mechanical engineering, and that it's not just limited to what a lot of people believe mechanical engineering is to be. So before I end off today, I just want to advertise our GirlCAD campaign that's run by the SciMechie student chapter. So the GirlCAD campaign is hosted at UKZN in the Mechanical Engineering building in collaboration with the SciMechie student chapter. And the aim of this initiative is to give girls and students from girls' schools a crash course in engineering, graphics, and design to prepare them for the first year of university. So it's still quite common that a lot of girls' schools do not offer EGD. So this gives ladies who are interested in engineering the opportunity to be on the same footing as men when they come in to study engineering, and it promotes women in STEM. So this is available to grade 10s, 11s, and 12 learners. It's a free program, and it runs over the course of 3 successive Saturdays. So you get to work in our LAN, you get to experience using some of our software, and we teach you the basics of EGD. So I've mentioned before the possible careers that you can use in engineering or can follow in engineering, but with the ability to use CAD software, computer-aided design, that's not just limited to engineering. You can also look at architecture, interior design, game development, drafting, jewelry design, and the fashion industry. So as I mentioned, it's run here in our Fenterland in the mechanical engineering building. We've already run our first workshop in April. Our second workshop is running in September, the 10th of September, the 17th of September, and the 24th. It's usually about a 3-hour program per day, which involves a small lunch. So if any ladies who are watching today are interested in joining the program, as I mentioned, it is a free workshop over the course of 3 successive Saturdays. You are welcome to email girlcad@gmail.com for more information. So I hope everybody enjoyed the presentation today, and thank you very much for allowing me to give everybody an idea of what mechanical engineering and being a student in mechanical engineering can be like.
Oh, thank you, Ingrid, with your presentation. We have prizes, 3 prizes. Maybe you can ask maybe 3 questions, and whoever gets it right, they will get the prize.
Sure thing. Alrighty, so so I showed an example of the Mimosa pudica plant, which is able to close its leaves when it's being touched. What is a common name for the Mimosa pudica plant? Do I select the
Yes, yes, you can select, so whoever raised their hand up.
Okay, Vardhan Maharaj.
Ma'am, did you say it was the shame plant, I think?
Sorry, can you repeat that?
Did you say it was the shame plant?
That's right. That's correct. Well done.
Thanks, ma'am.
Varen, can you please share your cell phone number with me on the group chat?
Okay, so next question. What year did UKZN take part in the International Solar Car Challenge? Okay, we've got 1 hand up. Just trying to just correct me if my pronunciation is incorrect, but Shemay Lynn Govender.
For the year 2020.
Can you repeat that? Sorry, Shemay. 20?
20.
Sorry.
It sounds like she was having internet connection. And she's already won the prize the previous days. Maybe you can try another one.
Okay, Yashoda Govender.
Was it 2021?
Not quite. So that was the ASRI rocket launch. So anybody else want to go? Let me change up the question a bit. In what country did the international championship take place? Piwe?
Was it Australia?
That's right. Well done. And one last question. Let's have a think. How many volts that was required to run the dielectric elastomer? Yashoda?
Was it 5,000 volts?
That's right. That's correct.
Can those who won please share their numbers with me on the group chat? Thank you, Ingrid.
It's a pleasure. Thank you very much for having me. Keep well, everybody.
Bye. Everyone, that's the end of our session today. Please join us tomorrow. Tomorrow is our last day and we will be doing probability. And we also have a science show by Dr. Tanya from UKZN, and we also have lucky draws. Shemail and the winners will be contacted once the program has ended, once we have grouped all the winners for each day, probably next week. Yeah, next week. Siyabonga, thank you. Isiyobonana kusasa. Simo uthe kusasa you'll still be in his place since he's busy next class.
Oh, yeah. Yeah, I will.
Okay. Yeah. Bye.
All right. Bye, Sneh. Bye, everyone.